Hey y'all, so I know we've kind of broken up what we're doing today into two different parts here. We got this little bit of a review, and then you guys have a quiz, and then we're going to do a little tutorial on how we do some calculation problems with wavelength, frequency, and energy for electromagnetic waves. So to start off with a little bit of review, last time I had you guys kind of filling out this sheet here, and hopefully you guys were all able to do that and had fun kind of playing with the simulation. I think it's kind of cool, neat little things. Now, the main thing I want to touch on were some of these post-lab questions to make sure you guys are coming away with the right things there. So this first one, why does water's response to microwaves help explain how microwaves heat food? Well, if we look at this here, and if I turn on my microwaves and put on water there, and water is not the only molecule that does this, that reacts to microwaves in this way, but you see, if I were to describe what's happening, right, it starts kind of rotating, and then it starts re-emitting those microwaves. So picture that you have something in a microwave that's full of water molecules, and all of a sudden all of those water molecules start spinning and rotating all at once, right? Well, all of a sudden they've gained a lot more kind of molecular, right, heat energy, right, which is the movement of these molecules. So all of a sudden that water, that food gets really, really hot, and so that's how microwave can heat food so quickly, right? Is because of how these microwaves, right, how the water actually reacts to those microwaves, right? It can respond to them because it's the right size, it's got the right polarity that it happens to kind of rotate around when it's exposed to microwaves. Okay, so that's one. The second one, B, right? Earth's surface radiates off infrared wavelengths, right? So as Earth's surface heats, all warm things above 0 degrees Kelvin, above absolute zero, radiate off infrared waves, right, to get rid of some of that heat, to kind of dissipate it. So the Earth does this, and so it kind of radiates some of the excess heat, and a lot of it ends up going up into space, right, and just kind of leaving Earth as a whole, never to return, right? But there's certain molecules that we can put up there. Water is one of them, right? And carbon dioxide is another, right? Where when they're exposed to this infrared wavelengths, right, these wavelengths of heat kind of that are leaving the Earth's surface, it gets excited, right? It starts vibrating a little bit more, okay, so it heats up, and then it re-emits infrared wavelength in some random direction, right? So this is why you might hear of carbon dioxide as a greenhouse gas, right? As this heat is trying to leave Earth, carbon dioxide kind of absorbs that heat radiation and reflects it back down. Now, oxygen and nitrogen, right, the two main molecules that make our atmosphere, don't actually do this, right? They just let the infrared radiation pass on by. So as we increase the percentage of carbon dioxide in our atmosphere, right, it kind of helps trap that heat in, which has some unintended consequences. If we look at C here, right, nitrogen dioxide is the only one of these molecules that has a color, right? And kind of the evidence for that is if we go to nitrogen dioxide, it's the only one of these that will actually kind of react, right, to visible light, right? All the rest of them don't actually react to visible light at all, which means that visible light just kind of passes right by them and they appear transparent, right? They're not able to reflect or absorb any of those visible light spectrums. So that's why nitrogen dioxide has a color. It actually ends up having kind of a reddish color in reality. And then this last question that we have is, why would ultraviolet light be harmful to the DNA in our cells? And what evidence in the simulation supports that? Well, if we go to ultraviolet, one thing that we notice is that with particular molecules, not with all of them, but with some of them that happen to have these kind of double bonds and a single bond, the ultraviolet radiation can actually, the ultraviolet wavelengths can actually break those apart, right? It actually shatters them. So thinking about like our own cells, right? If we have molecules that happen to have this particular bonding pattern, right? These ultraviolet, these higher energy wavelengths can actually break those apart, which can be bad. It can lead to mutations and other things, eventually leading to like cancer, which is not so good, right? So hopefully you guys kind of got some of that from those questions. If not, now you know. A few last pieces to kind of review and touch on. Woo, not there yet. First is kind of going along with that ultraviolet radiation, breaking apart those molecules. I want to bring up, this will be useful for your quiz, this idea of ionizing versus non-ionizing radiation. One thing I noticed in your guys' videos when you talked about the form of electromagnetic wave that you guys researched is one of the things I asked is it kind of dangerous? And a lot of you guys had kind of mixed results on this, and I do want to kind of clarify this a little bit. So there's two main ways that we can break up radiation, or these electromagnetic radiation. One is we can say that they're ionizing. Now in this case, ionizing radiation, these are high energy wavelengths like ultraviolet, X-rays, gamma rays, right? So higher frequency, higher energy, and they can ionize, right? Now what that looks like is essentially when that radiation comes in, right, it can hit an electron orbiting around an atom and it can knock it free, it can knock it loose. Now, if an atom loses an electron, right, then it becomes more positively charged, so it becomes an ion. It becomes a positively charged ion, and that electron becomes a negative kind of free radical. So this can actually cause some serious chemical changes, chemical reactions, and other things that we don't necessarily want. But this is fundamentally different than non-ionizing radiation, right? Non-ionizing radiation doesn't have enough energy to knock those electrons free, right? So this is like visible light, infrared, microwaves, radio waves. They don't actually have enough energy to knock things free, to knock those electrons free. They can heat up molecules, as we know. Microwaves can definitely heat up molecules. Infrared can definitely heat things up, right? Radio even can heat things up a little bit. But they don't really have quite the same effect as these ionizing. So these ionizing certainly can be quite dangerous, right? Ultraviolet, just thing there. It's like, sunscreens. You need that to prevent from like skin cancer, X-rays. You guys have probably heard how you can get cancer from that. Whereas these non-ionizing radiation, they can heat up, and there's not as strong of a link or a connection in current research to suggest that they actually have any serious long-term side effects. But they can certainly, warm parts of your body up, right? You wouldn't want to stick your hand in a microwave while it's running. That could actually be incredibly dangerous for your hand, right? So that's a little note on ionizing versus non-ionizing radiation. It has to do with the energy level, right? And this is a big difference in those different wavelengths. And another thing I wanted to bring up is that there is a whole spectrum, right? Don't forget, we just kind of went over those 7 kind of main categories, but and then we can kind of see them here, right? And we got a general idea of the size of the wavelengths, and we see it's kind of like a spectrum kind of between those. But I do want to point out, it's like, yeah, there's a whole range and a whole variety of different radio waves, a whole range and variety of different microwaves that we can classify in different ways. So for example, we can break up, even just visible light, right? We can break that up into the different colors and their constituent wavelengths that represent those colors that we can perceive with our eyes. Similar with radio and television signals, right? They actually break those up into different channels. And similarly, like the dials on your radio, right? If you think about it, right, all the frequencies on the dial of your radio as you're changing, each station is on a different frequency, right? And just think of how many of those there are, and that's just a tiny little slice, right? So there's a ton of these different frequencies. It's a whole spectrum all the way across, right? So kind of going off of that, how exactly do we use like radio waves, microwaves, infrared waves to communicate and send information? So how do I get a TV signal? How do I get a cell phone signal? How do I get a radio signal, right? Well, I kind of went over this a little bit the other day, but I have this little simulation here, which kind of shows we have a kind of radio tower there, or a TV tower. Now, you guys have probably seen these before. They look something like this. They come in all sorts of different shapes and styles, but they're incredibly tall, actually. This is for WDSUs. It's their TV tower, and so they use this to actually broadcast a television signal that you can pick up with an antenna on your TV and get like cable television. Okay. Now, if we actually look what's happening, right, we're essentially sending a charge up and down that pole, right, sending an electron up and down that pole, like through a wire, right, and as that electron accelerates, right, it sends out this electromagnetic wave, and this electromagnetic wave has a particular frequency, okay, that it sends out. It sends out through space in all directions, right, and it's quite large. It can travel around a lot of things. Can't go through mountains, but a lot of times, these waves are so big that they can go up and over mountains. And what you end up getting then is at your car or at your house, right, you have a receiver. And this receiver can be tuned, right, to pick up the exact frequency of the signal that's being broadcast, right? So it's very similar to what we did with our little telegraph with the wire moving the magnet. However, in this case, we don't actually need that direct wire connection, right? We just have a big kind of antenna sending a signal and then another antenna that can pick it up, that is very finely tuned to be able to see and pick up and is sensitive to these electromagnetic waves. So when you turn the dial on your car, right, to change the station, what you're doing is you're essentially fine-tuning your antenna so that it's looking for different resonating frequencies, right? So if I change the frequency of this, right, then the frequency of this needs to change to pick up that signal, right? So I need to kind of tune my antenna to pick that up. And the last little thing, if you guys don't know that, that's really all that you guys need to know from this video. But I did want to talk about chlorophyll and the absorption spectrum, right? So this is kind of a cool thing. We all know about photosynthesis, right? These plants absorb energy from the sun and they use it to make sugars. But this is actually the absorption spectrum for the two different types of chlorophyll pigments that are used in photosynthesis. It looks like this. There's chlorophyll A and chlorophyll B, right? And you can see that there's this big spike, right? They absorb a lot of those wavelengths of light. They take that energy in and use it to make sugars, convert it, right? Around the blue and the violet, right? And then there's another solid spike around kind of the orange and the red, right? And so this is the visible light spectrum, kind of going from 400 nanometers to 700 nanometers, right? Beyond is infrared, and then on this side is the ultraviolet. So they use these wavelengths, right? They absorb that energy and use it to make sugars. But within this green and this yellow range, right, they don't really absorb those, right? What actually ends up happening is that those pigments in the plant surface, they actually reflect that, right? So that's why we see these plants, these leaves as being green, is because the green wavelengths are not actually able to be absorbed, they're just reflected off. Whereas the other wavelengths are actually absorbed and the energy is then transferred into the chemical bonds within those sugars. So that's kind of a cool thing, right? Thinking about how these electromagnetic waves are generated, and then how they are essentially received by other matter, and this energy kind of cascades along and is transferred. It's really quite a fantastic thing. So that's really all for this video. Good luck on the quiz. I hope you guys rock it. Like I said, take as many times as you need. Get 100%. Open note, open book. I believe in you guys. After that, video 2 coming up to do a little tutorial on some little maths problems using wavelength, frequency, and energy.